We're finally going to get into an ecology chapter, so let's look at chapter 33, Population Ecology, to begin with. So just by definition, ecology is the study of the interactions of organisms with each other and with their physical environment. Modern ecology focuses on developing testable hypotheses, and one goal of ecology is to develop models that explain and predict the abundance of populations. Levels of organization. So when we talked about levels of organization from atom up to organism, we talked about atoms go together to make up molecules, molecules make up organelles, organelles make up cells, cells make up tissues, tissues make up organs, organs make up organ systems, and organ systems make up organisms. So we have the same type of a scheme in the organization of ecology, but we start off with an individual organism. An individual organism goes together with others in the same area to make up a population. Different organisms living together in different types of organisms living together in a particular area makes up a community, and all the communities together make up an ecosystem. So here's just table 33.1 from your textbook that gives you basic definitions. So ecology is the study of the interactions of organisms within their physical environment. Population is all the members of the same species in that area. Community, all the populations in a particular area. Ecosystems are the community and its physical environments, or the living and the non-living, or the abiotic and the biotic components, and then all the ecosystems on Earth and their biotic communities makes up our biosphere, and that means life sphere. Bio means life, so life sphere, which is the Earth. Section 33.2 is going to talk about patterns of population growth. So the growth rate is equal to the per capita rate of increase. So here's an example. Population has 1,000 members. The birth rate is 30 a year, and the death rate is 10 a year. So the growth rate per year is going to be the difference between the birth rate and the death rate, which is going to be 20 divided by 1,000, because that's your total, and multiply times 100. So the growth rate is a positive 2% per year in this population. Biotic potential is the highest per capita rate of increase for a population. There are factors that influence the biotic potential, such as the average number of offspring per reproduction. So whether an organism has 10 on average per cycle of reproduction, or 1 like humans do. The chance of survival until the age of reproduction, because the only way to make more organisms is to get them to reproductive age and allow them to reproduce. The age at first reproduction, of course, the younger they are at reproductive age, the quicker there are offspring available to increase the number. And then how often each individual reproduces, every 38 days, every 9 months, whatever it is. The faster it happens, the greater the number of organisms in a population could possibly be. There's exponential patterns of growth rate. So this results in a curve, and I'll show you a picture on the next slide, called a J curve, or J-shaped curve. There's also, and this is ideal growth, so it's unlimited. Lag phase is the growth is small because the population is small. We have exponential growth phase, where it's accelerating, the population is reaching its biotic potential. The whole thing is that we can't keep that exponential growth going because of environmental resistance. So here's a picture of number of organisms on the y-axis, time on the x-axis. Here's your lag phase. You have a small number of organisms. It takes a little while for them to reproduce, and then they reproduce exponentially, and nothing's stopping their reproduction. So they have plenty of resources that are allowing them to go ahead and reproduce. This is a J-shaped curve. Logistic growth. Intensity of environmental resistance increases as the population grows larger until the population levels off, and this forces that J-shaped curve into an S-shaped pattern. And there are 3 phases in that S-shaped pattern. Stable equilibrium phase is said to occur at the carrying capacity of the environment. The lag phase in an S-shaped curve, growth is small because the population is small. Then you have the exponential growth phase, and this is where the growth is accelerating, the population is trying to reach its biotic potential. Then you have the deceleration phase, and this is the rate of population growth is going to start to slow down, so we start to see a turn in letters from the J to the S shape. And then you have stable equilibrium phase, and this is little if any growth takes place because the birth and the death rates are just about equal. So here's our J-shaped curve that we saw a while ago. And we start to see the same thing happen in the S-shaped curve. We have exponential growth, but we start to see a deceleration at this point, and that's because we're starting to reach the carrying capacity of the environment that the organism is in. So normally what's going to happen is if you have a lot of unlimited resources at this point and you have exponential growth, a lot of reproduction happening, a lot of offspring surviving, you have an increase in the number in your population, and you start to have some issues with the environment being able to sustain as much as it can, and this is where the death rate and the birth rate tend to start leveling off. And now this level is never completely smooth. There'll be an increase, it'll go above the carrying capacity, and then the death rate will increase and take it below the carrying capacity. So the stable equilibrium, we would expect to see it like this. So this, we have the J-shaped curve with exponential growth and the S-shaped curve with more logistic growth. Survivorship. Growth curves assume all individuals are identical. In real life, we realize that that's not true. Individuals are at different stages of life. Cohort are groups of individuals born at the same time. So we would call these generations, like Generation X, as you're familiar with, or the baby boomers. So the plotting the number of surviving over time gives us a survivorship curve. So here we have a picture of this. We see the oyster has, and we're going to talk about the different types of survivorship curves, has a type 3, a songbird, a type 2, and a human, a type 1. So this is percent of the lifespan and the number of survivors, and we'll explain those as we go through the different curves. Let's look at survivorship type 1. This is when most individuals survive to an old age. For the example, was the humans on that curve. Survivorship 2 decreases consistently over time, like songbirds. And then type 3 is most individuals die at an early age. So let's go back and look at that picture again. And we see the different types of survivorship curves here again, with humans being type 1, where most of them live to old age. Songbirds, it's a decrease, gradual decrease throughout their lifetime. And oysters, most of them die off at a really early time in their lifespan, and very few of them make it to old age. Human population growth is one that everyone seems concerned with, and of course, the more people we put on this earth, the more we wonder what is our carrying capacity and how much can the earth tolerate. So human population growth, right now there's approximately 220,000 people added to our population each and every day. That's about 82 million people added every year. The current doubling time is 52 years. So remember, the doubling time is how long it's going to take for our population to double its size. So at this growth rate, they think that we will double our size in 52 years. So the world's population, we expect to see level off at 10, 12, or 14.2 billion, just depending on the ability of us to sustain that many people. This is from the Population Reference Bureau, and this is population in billions. The blue is the less developed countries, and the purple are the more developed countries. So we take a look at the information here. It's quite fascinating to me. So that we're talking about 1750 up to 2150. So we have projected, because we're back in here around 2000, a little over 2000, 2014 right here. And we can see from the graph that we see a gradual increase in number around 1950, 2000. So we're increasing. We see a little bit of a dip down projected here around 2050 to 2150. Did you notice what happens to the world's population when we look at the less developed countries? We see this huge increase in world population due to less developed countries. And we're going to talk about the reasons for that. Human population growth. In more developed countries, we refer to these in your textbook as MDCs, population growth is low and the standard of living is pretty high. So the demographic transition increased rapidly between 1850 and 1950 due to a decrease in death rates and modern medicine, which should make sense because the more technology that we have, allowing us to make better medicines and allowing fewer deaths to occur due to that. That's just one of the many reasons. The transition from agricultural to urban society lowered birth rates as well. Population growth in more developed countries has stabilized, so more developed countries are about 0.1% in growth rate per year. Germany, Hungary, Italy, Greece, and Sweden are actually decreasing in size. In the United States, our birth rate is 0.6%. however many people immigrate to the United States each year. So we not only have to take into account when we're looking at the United States population, not just births and deaths, but also immigration and immigration as well. In less developed countries, or LDCs, population growth is expanding rapidly and the standard of living is low. So the populations of the lesser developed countries could reach 11 billion by the year 2100. Most of this increase we see in Latin America, Africa, and Asia. So the ways to decrease this expected growth are to establish and strengthen family planning programs, use social progress to reduce desire for large families, and delay onset of childbearing. Here we have an age structure diagram for less developed countries and for more developed countries. So in lesser developed countries where they have a really high birth rate, you notice here that we have a lot of pre-reproductive ages, so a lot of younger children, a lot in the reproductive ages, although there are more at the bottom than there are here at the middle. So this means that this group eventually will become reproductive, and they will probably put a larger base on their pre-productive offspring because there'll be so many more of them. And then we have the post-reproductive ages, so the older people up here. So we see this larger base of young people and a smaller base of older people. You look at more developed countries, such as the United States, we don't see that pattern at all. In fact, we see a lower number of younger children, and then we have the reproductive years and about the same number. So we're starting to see this level off to where we have almost no growth overall. This is called zero population growth, which means that you would only replace your life. So if you have one life, you're not going to have 4 children. You're only going to have 1 child to replace you. So a couple would only have 2 children max to get overall population growth of 0. And you notice too that our older generations, we're starting to see an increase in that as well. As many older as we have the middle class that's still working, which is a Social Security issue on top of that. So lots of differences in the age structure diagrams between the lesser developed countries and the more developed countries. That's going to conclude the first 2 sections of this chapter, so let's do some activities in class that will help reinforce these ideas.